Guys. We're going to talk about multiple event probability today. Not much is going to change about this other than, kind of the situations we're going to be presented with, but the math itself is going to be the same. Your basic thing that you're going to have to do is your desired outcomes over your total number of outcomes. Okay, so if you don't understand what I mean by that, go back and watch the old videos. Go back, watch the videos from the last week, do those first, because you're going to be so lost with this if you don't understand what I'm talking about there. Okay? So there's videos, I moved them on the website. There's a link there, you guys should be able to find it. Okay? But what's going to happen is we're going to have multiple events. More than one thing are going to happen, and there's two different situations we're going to look at today. It's going to be independent events and dependent events. Okay? So let's give you a quick example. Coin flip experiment, right? So if I flip the coin once, right, my probability of getting heads is 1 out of 2, right? Now I expect though, if I did that again, right, if I did this multiple times, what's my probability of getting heads the second time? And you would think, right, like, well, we got the heads that we wanted. The second time, it should be less likely. That's not true. The second time I do it, I get the probability of getting heads is still exactly the same, okay? And this is a tricky idea, and it leads to what's called the gambler's fallacy, a fallacy meaning something that's false. So the gambler's fallacy pretty much says that, you're due, right? Like you're due to get the heads or tails. And that's not true, right? So if you were playing the game, right? So if I said, what's your probability of drawing a king, a 5, a 7, a 2, and a jack, right? The probability of that, you think, should be different than the probability of getting a 1, a 2, a 3, a 4, and a 5. The probability of these two things happening are exactly the same. Even though this seems much more random, it has the same chance as this happening, okay? And each successive card deal really doesn't have any influence on the one before it. Now, here's where it gets tricky, because we also have the law of large numbers, which says if something is done and it's fair, the more times we do it, we should expect it to come out as the results we want. So this is why you always hear in card playing movies and stuff like that, if you can outlast the casino, and it is true. I don't gamble, so I don't I don't prescribe to any of these theories. But what we want to talk about is independent events and dependent events, okay? Because they're very much related to what we're talking about. So in a coin flip, the outcomes are unrelated. In other words, each time I flip the coin, right? So that coin flip we're looking at, right? So if I said, hey, what's your probability of getting heads? It's 1 out of 2. I do it a second time, what's your probability of getting heads? It's 1 out of 2, right? It doesn't change, right? If you roll the die and I said, what's your probability of getting a 4? Well, there's 1 4 on the die and 6 times. What if you rolled it again? What's your probability of getting 4? Doesn't matter. Same thing. It's 1 out of 6, right? So these are independent events, meaning that they have no influence on each other. So they might say, roll twice, right? Roll twice. What's your probability of getting a 4, then a 4 again? So what's your probability of getting a 4, then getting another 4? Well, pretty straightforward. What you have to do is you have to say, what's your probability of getting a 4 on the first die? It's 1 out of 6. What's your probability of getting a 4 on the second die? 1 out of 6, okay? And very simple, the fundamental accounting principle, which is something we talked about, all you do is multiply. And I know a lot of people freak out when they see fractions. Remember, you just multiply the tops and multiply the bottoms. The worst thing you're going to have to do is break out your calculator. So 1 times 1 is 1, 6 times 6 is 36. And what does this tell you? That there's one way to get your desired outcome, that's a 4 and then a 4, and there's 36 total different outcomes you can have, okay? Same thing. What if I said 2 flips, okay, and you want both heads. Again, your probability of that, so we'll say probability of heads, then heads. Well, what is that? That's 1 out of 2 the first time, and 1 out of 2 the second time. So that's 1 out of 4, right? So that's your 1 desired outcome over your 4 total outcomes. And this is a little bit easier. I don't have to list 36 of them. Your 4 outcomes were, well, heads and a heads then a tails and a heads and a tails and a tails. Those are your only 4 different outcomes you can have, right? Well, heads and heads represents one of those, okay? Now, dependent events are a little bit different. So coin tosses and dice rolls are not dependent events. This is something like you pull a card from a deck. Okay, you pull a card from the deck, and don't replace it. You'll see the word replace. Don't replace, okay? In other words, you're taking the card of the deck and you're not putting it back. So if I said, hey, what's the probability of pulling an ace, then a king? Right, well, again, if you guys aren't familiar with the deck cards, hold on, I think I have one here. Okay, you have 4 aces, right? You have 4 kings, okay? So what's your probability of pulling an ace? Well, on your first draw, your probability ace, then king. Well, again, your first event, you have 4 aces out of the 52 cards. So your probability of pulling an ace is 4 out of 52, same as any other card. There's 4 of each one, there's 52 cards. But that second number now, watch out, once you've taken one of those aces out, so say I got the ace of clubs, right? You have to assume that you've got one, otherwise you can't proceed. Well, how many kings are left in the deck? There's 4 kings, but now there's only 51 cards, okay? So now, again, I don't know what 52 times 51 is off the top of my head. Maybe you guys do, but maybe I'll break out our calculator just in case, okay? So again, well, 4 times 4 is 16, right? That's the easy part. 4 times 4 is 16. And 52 times 51 is 52 times 51 is going to be 2,652. 2,652, okay? Meaning if I pull 2 cards, there's 2,652 different outcomes. 16 of them have this. And again, if you want to evaluate that, you break it in, say 16 divided by 2,652. So you saw, and that's a 0.006. 0.006, which means this is a unlikely thing to happen, 0.6%, okay? But believe it or not, there's just as well as a possibility of pretty much anything except for pulling 2 cards in a row. So these situations, whether they're independent or dependent, they have the same kind of thing. You're just going to multiply fractions together. It's just you have to watch, hey, did the first outcome have an influence? So here, yes, the first outcome had an influence because there's 1 less card in the deck, right? So a big thing you'll see are card pulls and bags of marbles, okay? So I said, hey, what's the probability of blue, then blue? Sorry, that's terribly written. And we're going to say without replacement, meaning you're taking the marble out and you're not putting it back. So again, your probability of pulling a blue, well, I've got 1, 2, 3, 4, 5, 6. And there are 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So your probability of pulling the blue on the 6 one, 6 out of 20. Now the second time, since you're keeping that blue marble out, there's only 5 blue marbles out of the 19 marbles that are left. Okay? 5 times 6 is going to be 30, and 20 times 19 is going to be 380, so that's a 3 out of 38 chance that that's going to happen. Okay? So we'll take a look at a couple examples, and I'll set you guys loose. Okay? So it says bag A contains 9 red marbles and 3 green marbles. Bag B contains 9 black marbles and 6 orange marbles. Find the probability of selecting 1 green marble from bag A and 1 black marble from bag B. Again, since the 2 bags are completely separate, what you pull out of the first one has absolutely nothing to do with what you do out of the second one. Okay? So bag A contains 9 red marbles and 3 green marbles. So that's 12 altogether. 9 plus 3 is 12. So what's the probability of pulling a green marble? Well, there's 3 green marbles out of the 12 total marbles. So that's, so say the probability of green then black. Okay? So the probability of green on the first one is 3 green marbles out of 12 total marbles. Okay? And in the second one, you have 9 black marbles and 6 orange marbles. So there's 15 altogether, right? 9 plus 6 is 15. And that's 9, right? So 3 times 9 is going to be 27, and 12 times 15 it's going to be 180. All right, again, if you want, you can reduce that. You can say what's 27 divided by 180. I'm sorry, simplify that and say that is a 0.15 or 15% chance of happening, right? So again, independent events. It says 2 seniors from each government class are randomly selected to travel to Washington, D.C. Wes is in a class of 18 students and Maureen is in a class of 20 students. So they're in 2 different classes. Find the probability that both Wes and Maureen will be selected. Well, probability of Wes and Maureen. Well, Wes is 1 out of 18. And Maureen is 1 out of 20. So 1 times 1 is 1. And 18 times 20 is going to be 900, I think. Sorry, my brain is a little fried some of the day. 360. Way off, okay? So that's a 1 out of 360 chance. So 1 out of 360 leads us to about a 0.0027 repeating chance, okay? Or about a 0.27% chance. So not less than 1%. Really bad chances it's going to happen. So sorry, guys. Okay. Dependent events, right? So these are going to influence each other. A box contains 5 purple marbles, 3 green marbles, and 2 orange marbles. 2 consecutive draws are made from the box without replacement. So you're taking it out and you're keeping it out. Find the probability of an orange first and a green second. So again, there's 5, 3, and 2. So there's 10 marbles altogether. So on your first pull, orange, 2 out of 10. On your second pull, since you're not replacing it, there's only 9 marbles left, and that's going to be a green, which is going to be 3, okay? You can always reduce these beforehand, so you could say this is 1/5 if you'd like. 1 times 3 is 3. 5 times 9 is going to be 45, so not very good chances. You can reduce that further. I'm sorry, I should have done that here as well. That's going to be 1/15. Okay, and again, if you want to turn that into a decimal, 1 divided by 15, you're going to find that that is a 0.06 repeating, which is 6.6 repeating % chance of happening. Okay, what's the probability that both marbles are purple? So again, there's 5 out of 10 on the first try, but on the second try, well, you have 1 that you took out, so there's 4 purple marbles out of the 9 that are left, okay? So again, you want to reduce this in advance. You can say this is 1/5, and you can say that that is a 4 out of 45 chance, which is 0.08 repeating, which is about 8.8%. Okay, so I left you guys the IXL skill. Give it a try, and I'll talk to you tomorrow.